Welcome to section 14.7. In this section, we're going to be using the concept of partial derivatives to identify extreme values. So that'd be maximum and minimum values for functions of two variables. We're going to see ways in which it is similar to what we've done in single variable calculus and ways in which it differs once we move into the third dimension. So right out of the gate here, so we say a function of two variables has a local maximum at a value ab if f of xy is less than or equal to f of ab when xy is near ab. So the output at ab is bigger than the outputs near ab. Okay, so the output at AB is larger than the outputs around it. That makes it a maximum, okay, a local maximum. And the number f of AB, whatever that output is called the local maximum value. Okay, so the maximum occurs at AB. The value is f of AB. Similarly, if f of AB is smaller than all of the outputs near AB, so if f of AB is smaller than everything in its immediate vicinity, everything around it, then f of AB is a local minimum value. Now, if you recall from like Calc 1, when you learn how to find maximum and minimum values for a single variable function, we need to take the derivative, set it equal to 0, and find those critical points, those critical values or critical numbers, depending on how you learned it. It's going to be a similar concept here. So if f has a local max or min at a point AB, and fx and fy exist there, then, sorry, this gets kind of cut off here. I'll just put it down here. Fx of AB equals 0, and Fy of AB equals 0. So if there is a local max or min at a point, and the partial derivatives exist, those partial derivatives will be equal to 0. And this point AB is then called a critical point. So it's a critical point if fx equals 0 and fy equals 0 at the point AB, or if one of these partials does not exist. Now, just like when we learned this in Calc 1, this theorem tells us that if there is a local max or min, then it's a critical point. It does not necessarily go the other way, okay? So this theorem tells us if we know already that this point is a max or a min, then the point will also be a critical point. This doesn't necessarily go backwards, so not all critical points are maxima and minima. Okay, so we can't say if it's a critical point, then it's a max or a min, because that is not a guarantee. Now, how could we identify local maxima or minima for a function without using the concept of the critical point? Okay, because this tells us right now, temporarily, that critical points do not guarantee maxes or mins. So we could go about this with a slightly different, more algebraic approach. If we go ahead and take the partial derivatives, so we've got fx of xy, that's 2x minus 2, and we've got fy of xy is 2y minus 6. So if we're looking for critical points, we're going to set these equal to 0 So we get x is 1 and y is 3. So the only critical point is at 1, 3. Now, just because it's a critical point does not guarantee that it is a max or a min. So we have to ask, is this a max or a min? So to figure this out more algebraically, we can take a look at the function again. So we got the function right here. What I want to do is I want to regroup and put the x's together and the y's together. So let's kind of just separate this off here a little bit. So f of xy equals x squared minus 2x plus y squared minus xy plus 14. What we're going to do with these groupings here is we're going to complete the square on both. So if we do that, we end up getting x minus 1 squared plus y minus 3 squared plus not 14 anymore, because in order to complete the squares, we had to add 1 and 9 here. So to keep it balanced, we needed to take 9 away from here. So we get this new function. So this is the same f, just rewritten, kind of reorganized. Now the question is the point 1, 3 a maximum or a minimum? So notice what these terms are here now. For the x terms, we have x minus 1 squared. For the y's, we have y minus 3 squared. And then we have the plus 4 out here. So we can say, since x minus 1 squared will be greater than or equal to 0 always, because it's squared, and y minus 3 squared will be greater than or equal to 0 for the same reason, then the function, if this one is always positive, this one is always positive, then if they were 0, right, the smallest they could be is 0 for both, and the value of the function would be 4. Or it could get higher as these values start climbing up, but the function will be greater than or equal to 4. Okay, so the smallest value this function can take on is 4. When f of 1, 3 equals, that's 0 plus 0 plus 4. So f of 1, 3 is 4, and the function will always be greater than or equal to 4. We can say, thus, the point 1, 3, 4 is a local minimum. So we have a local minimum, okay, found by understanding the relationship between the values of x and y in this function by reorganizing a little bit. Now, let's take a look at one that's a little bit different. And I've got some stuff written here ahead of time, but you can kind of fill those in as we go here. Find the extreme values of this function. F of xy is y squared minus x squared. If we go ahead and take the partial derivatives of this, fx is negative 2x, fy is 2y, and we set both of them equal to 0. There's only one outcome of this, right? So our only critical point is 0, 0. It's the origin. Now, if we were going to try to reason through what happens to this function around this point, let's look at a couple different directions, a couple different approaches. So we're going to start looking at some of my filled in stuff over here. So notice as we approach along the x-axis, so we're getting closer and closer to the origin along the x-axis. That's the line y equals 0. We get f of x comma 0, because y is always 0, equals negative x squared. Right? And this negative x squared value will always be less than or equal to 0. So we know as we're moving along the x-axis, all of the values are going to head down. They're going to drop, okay? And it's parabolic, so they're going to go kind of like that. Now, if we approach along the y-axis, so that's where x equals 0, we get f of 0 comma y. So we get y squared minus 0, so just y squared, which will always be greater than or equal to 0. So along the x-axis, it was going like this. Along the y-axis, it's going like this. So we have some values in one direction that are all below 0, 0. And we have some values in the y direction that are all above 0, 0. Some positives, some negatives. And that creates an issue. So since some values near 0, 0 are negative, that was from this first case, and other values are positive from the second case, it cannot be an extreme value. So we cannot have an extreme value on this function because the only possible choice was 0, 0, right? That was the only possible outcome where we had a max or a min would be at this critical point. But the critical point is not an extreme value, and there were no other choices. So we can say, thus, f has no extrema. So there are no local maxes or mins on this function. Now, I want to go ahead and pull up a graph of the function. I want us to look at it. So you can see here, I've got the point 0, 0 in green there at the origin. And when we look along the x-axis, so that's down here, you can see the orange curve. That's that downward parabola. When we look along the y-axis, you can see that upward parabola, right, going up. So you've got values in one direction going up, values in another direction going down. Because if it was just based off of the red parabola, the upward one, it would be a minimum. If it was just based off of the downward parabola, the orange one, it would be a maximum. Unfortunately, because it is not the smallest thing in its vicinity, and it's also not the largest thing in its vicinity, it has to be neither a max nor a min. Because if we were just looking at it from the perspective of the red curve, it's a min. And if we're just looking at it from the perspective of the orange curve, it's a max. But it fails to completely satisfy those conditions. So this would be neither. Now, this type of point does occur pretty frequently in functions of two variables. So it gets its own name, its own special type of name. And it's actually based off of a graph that looks like this, where it is called a saddle point. So you can see this kind of looks like a saddle a little bit. So you have the part in here would, sit down on the horse, and then these sides would be like where your legs would swing over. So it looks like a saddle. So this, if we go to the top of the next page, the type of point described in this previous example is called a saddle point. Saddle points are essentially the higher dimensional version of neither. So we have this as a possible outcome now in these local extrema tests. So we could get a case where it is neither a max nor a min, and it ends up being a saddle point. Now, we don't want to have to keep reasoning through our extreme value tests like we did in these two examples back here. We want to have a definitive test like we did in Calc 1, right? We had the first and second derivative tests for maxes and mins. Well, it turns out we do have one in Calc 3 as well. This is the second derivatives test. And the second derivatives test says, suppose the second partial derivatives of f are continuous near the point AB, and suppose fx and fy are both 0. Let d equal, so this is d of AB, so evaluate it at the point, equals fxx of AB times fyy of AB minus fxy of AB squared. So we have fxx times fyy minus fxy squared. This is a formula for D for derivative test, also called the D test. Now, what this value gives us is the following potential results. If D is greater than 0, so you can see these first cases A and B. If D is greater than 0, this tells us one of two things. This tells us it is definitely either a max or a min. Okay, if D is positive, that means it is a max or a min, but we just don't know which one. That all depends on the value of fxx. So if D is positive and fxx is also positive, then our value is a local minimum. If D is positive and fxx is negative, then we get a local maximum. Okay, so these are the max and min cases. We're looking for D to be positive to have a max or a min. If D is negative, no further testing necessary. If D is negative, that tells us automatically that the value is a saddle point, which again is kind of like the neither case, neither a max nor a min. So these tests here, if you want to think about them in relation to like the Calc 1 second derivatives test, where we looked at fxx being greater than 0, that picture that like the concavity. So this would be like a concave up type graph. So our critical point is down here at the bottom. That's what makes it a minimum. And then if fxx is negative, that's really like concave down. So our critical point is up here at the top, which is what makes it a maximum. So it's similar reasoning, but of course in a 3D sense rather than just a 2D curve. Now we left out one value. We said if D is positive, it's one of these two. If it's negative, it's a saddle point. If D is 0, then this test is inconclusive. So that's the case that we're hoping not to encounter, because if it's inconclusive, then we can't use the test. It's not that it means neither. It's not a result of saddle point. It means that this test cannot be used. Like, it won't help us in solving the process, in which case we would need to go back to some of the methods like from back here, where we try a more like algebraic or graphical approach to it. Those cases are, few and far between, but they can theoretically happen. And so we just wouldn't be able to use this test to do that. So it is important to remember the formula for D so that you can implement it. Sometimes people like to think of this in terms of a determinant. So if you remember determinants, we talked about them back when we learned the cross product a while back. So we can set up D as a 2x2 determinant, so a little 2x2 grid here with fxx, fxy, fyx, fyy. And if you recall, to take the 2x2 determinant, we do AD minus BC. So we get fxx times fyy minus fxy times fyx. Now this doesn't perfectly match, but remember, fxy and fyx, assuming we have continuous partial derivatives, these are the same by Clairaut's theorem. So we're throwing it way back to earlier, several sections ago in this chapter, to Clairaut's theorem. This is why we have fxy squared instead of fxy times fyx, because they're going to be the same thing anyway. So it is unnecessary for us to find both, because we know that they're going to be the same as long as the partial derivatives are continuous, which must be the case for this formula to work. So this determinant method, some people find it helpful, others don't. If you like it and this is an easier way for you to remember it, that's great. Go with it. If it's just more confusing than trying to just remember this formula up here, then don't worry about it. So it's just an extra aid. It's not necessity. All right. Let's take a look at an example. Find the local maxima, minima, and saddle points for this function f of xy equals x to the fourth plus y to the fourth minus 4xy plus 1. So first thing we need to do is locate the critical points. So we're going to take the partial derivatives. So fx, that's 4x cubed minus 4y, and fy is 4y cubed minus 4x. We're going to set these equal to 0. Set that equal to 0. Set that equal to 0. Okay, you can divide away the 4. You can add one value over, so you're going to get y equals x cubed. Now, if we take this, y equals x cubed, and substitute into this one, we get 4 times x cubed minus x equals 0. So this gives us, whoops, I don't need the 4 on there anymore. Just x cubed. So we get, that's x to the 9th minus x equals 0. So we can factor out an x, and that's x to the 8th minus 1 equals 0. This gives us a few possible outcomes. X could be 0, and then the x to the 8th minus 1. It's kind of like x squared minus 1 because it's an even power, but we would still get 1 and negative 1 for that. You could keep factoring this as a difference of squares. You can factor it actually several times, but you end up just getting multiples of the same values of negative 1 and 1. So we get these are our x values. The y values that go along with those, just cube them. So that's 0, 1, and negative 1. So that tracks, right? They're all the same value, because when you cube it for 0, 1, and negative 1, they just stay the same. So our critical points are 0, 0, 1, 1, negative 1, negative 1. So these are the values we're going to be testing. Okay, so these are the values that could be maximum or minimum values, but we need to check to see if they actually are. So next up, we're going to calculate D, so that derivative test. So we're going to need all of the second order partial derivatives. So let's go ahead and get those now. So fxx, that's going to be 12x squared. Fyy is 12y squared. And fxy is negative 4. So D will be 12x squared times 12y squared minus negative 4 squared. Be very careful with the negatives here. This is minus this term squared. A lot of times people, when they apply the square, they accidentally apply it to that and make it a positive, but it's not supposed to be. It's supposed to be minus whatever this was. So if we go ahead and simplify this a little bit, that's 144 x squared y squared minus 16. So that is our formula for D. And now we can test using D. So test all of these critical points. D of 0, 0. That's going to be 0 minus 16, so negative 16, which, of course, less than 0. D of 1, 1. We get 144 times 1 times 1, so just 144. Minus 16 is going to be 128, which it doesn't even really matter what the number is. All that really matters is whether it's positive or negative. And then D of negative 1, negative 1. We get, they're both squared, so it ends up being, again, 144 minus 16, which is 128. So that's positive. So the results here, the fact that this is greater than 0 tells us it's a saddle point. To say greater than, I meant less than. The fact that this is negative tells us it's a saddle point. These two could be maxes or mins because the value is greater than 0. We need to further check and see which one. So we're also going to take fxx of 1, 1. So that's going to be just 12, which is also positive. So that's going to give us a min as a result. And fxx of negative 1, negative 1. Well, the value is squared already, so it's also going to be 12. So that's also going to give us a min. So we have, let's see, we're looking for local maximum, minima, and saddle points. We have the classifications now. Let's go ahead and get the outputs. So outputs, so f of 0, 0. If we plug this back into the original function right here, that gives us just a 1. F of 1, 1. Plug in 1 and 1. Plus 1 is 3, minus 4 is negative 1. And f of negative 1 is also negative 1. So let's go ahead and draw our formal conclusions here. So we have a saddle point at 0, 0, 1. And local minima at 1, 1, negative 1, and negative 1, negative 1, negative 1. And then no local maxima for this one. So we have 1 saddle point and 2 local mins on this function. All right, let's take a look at the next example. So we're going to throw a little bit of a contextual problem in here. So a rectangular box without a lid is to be made from 12 square meters of cardboard. Find the maximum volume of such a box. So I have my box over here. So I went ahead and put on side lengths x, y, and z. In order to find the volume of the box, so again, we're looking for maximum volume. So that's going to be V equals x times y times z. So this is what we're trying to maximize or minimize, actually just maximize. What else do we know? We know that it's to be made from 12 square meters of cardboard. So we also know the cardboard, that amount of material, it would be the surface area. So surface area would be just, again, the area of all of the surfaces added up together. And again, there's no lid. So there's going to be an xy for this side and the back side. Excuse me, that's xz. xz for this side and the back side. Yz for the front and the back. And then xy is on the bottom. So there's going to be 2xz plus 2yz, so those are the 4 sides, plus xy is the bottom, and we know that that is equal to 12. So if we want to employ our test, our second derivatives test, and be able to actually determine max or min, we need to rewrite this in such a way that we can get rid of the z. We want to go ahead and just leave it in terms of x and y, or vice versa. You just get rid of one of the variables. So what we can do here is algebraically manipulate this a little bit so that I can get to the z. So I would subtract that over, factor out the z, and divide. We end up getting z is 12 minus xy over 2x plus 2y. Or 2 times x plus y, if you like. And we'll go ahead and put this in for z. So we're going to have xy times 12 minus xy over, again, that could be 2 times x plus y. So we've got 12xy minus x squared y squared all over 2 times x plus y. That's our formula for volume in terms of x and y only. Now, if we want to maximize this formula, we would need to take the partial derivative with respect to x, with respect to y, set them equal to 0 to find the critical points, and then test those critical points. Obviously, that's a bit of an extreme case in this example. And we're doing this example in particular because we're going to revisit it again in the next section as well, and we can look at another method for tackling this problem. But for now, this is, again, a pretty hefty amount of differentiation that would need to go on here because you would involve the quotient rule in this process. So I do already have some of this done for us. I'm going to go ahead and just kind of set this up. So to get Vx, we would set up the quotient rule. So you can see here, I've got low d high minus high d low all over low squared, right, with respect to x. So if we set up the quotient rule that way, it gives us this simplified formula that we set equal to 0. And then we could do the same thing for the y's. Again, I don't want to necessarily take up all our time to do that, so I went ahead and already did it. It works out pretty similarly. You can notice the only minor adjustments that went into that derivative. So we would set these equal to 0, and we would need to solve for x and y. Now, due to the context of the problem, we cannot have negatives or zeros, right? Because if x, y, and z are negative, then that doesn't make sense because it's the value, or excuse me, it's the length of the side of a box. So you can't have a negative length. And we can't have zeros because if it was 0, then the volume would be 0, right? If any one of these sides, then it's just a flat piece of cardboard. So we can't have 0 because that would not be a maximum volume to be 0. So with that in mind, we can go ahead and, if I can get this to shrink, there we go. So they're both equal to 0. And notice I multiplied the denominators away. And I divided away the x squared and the y squared out in front. Because again, cannot have negatives or zeros. So we can go ahead and divide those away. And that brings us to here. So when you set them equal to each other, the 12s, the 2xy's cancel, and you're left with x squared equals y squared, or x equals y. Again, it could, theoretically, it would be x equals plus or minus y, but we can't have negatives. So x and y will be the same value. So we go ahead and substitute back in. So I took x equals y, subbed in to here. That gave us this, which gave us x equals 2. So we got x equals 2, and since x and y are equal, that means y equals 2. And if we want to get the value of z, we go back up to here, plug in x and y both as 2. And we get z equals 1. So again, I skipped over quite a bit of the nitty-gritty algebraic details just because these ones are very heavy. But if you want to try out the algebra, you're more than welcome to. But this is what we get. So when it comes to these values and whether they result in maximum or minimum values, we can, so we can verify using D or argue intuitively in context that these produce a maximum volume. Okay, so, and again, in context, we know that the minimum volume here would be if x, y, and z were all 0, right? That's the smallest that it could physically, tangibly be. So this can't be the minimum. So we could argue that intuitively because of the context. Without that context, we would need to actually go through and show this. But again, it didn't ask, if we go back to the question, it didn't ask for the dimensions of the box. It asked for the maximum volume. So we're almost there. So the volume is just x times y times z is 4. So maximum volume is 4 cubic meters. And again, we will be revisiting this problem in the next section, looking at a different method to be able to solve something like this that doesn't involve us using, the quotient rule and all this kind of stuff to take the derivatives. So we'll see this one again in maybe a little more friendly terms. So the last major theorem for us to talk about in this section is the extreme value theorem. So the extreme value theorem, this is similar to the one in Calc 1 that you learn, but now it's been revved up, if you will, amped up in order for us to do this in 3D. So the extreme value theorem says that if f is continuous on a closed bounded set D in R2, then f will have an absolute maximum and minimum in D. Okay, so if f is continuous on a closed bounded set D in R2, then f will have an absolute max and min in D. Okay, so if we have an open region, it is possible that we might not have a highest and lowest absolute max and min. But if the region is closed and bounded, then there must be an absolute max and min. Kind of like in Calc 1. So if you have something like a curve that kind of goes like this, right, there must be, if it's closed, there must be an absolute highest, which would be here, and an absolute lowest, which would be down here on this function. If it's not closed, right, this could go on forever, then there may not be an absolute max or min. But that was Calc 1. In Calc 3, we're not working just with a curve, we're working with a region. So in order to find these absolute maxes and mins, we're going to find the values of f at the critical points in D. Okay, so any critical points that are within our region. Find the extreme values of f on the boundary of D. Okay, so we look at any critical points because those could produce maxes and mins in the region. And we need to look at the edges. So kind of like in Calc 1, they say look at the endpoints, right? Test your endpoints. Well, here it's not endpoints, it's a boundary curve. So once we find the critical points, we find the extreme values on the boundary. The largest of the values is the absolute max. The smallest is the absolute min. So we don't need to run a second derivatives test on these. All we need to do is find their outputs, and then whichever one is the biggest, that's the absolute max. Whichever one is the smallest, that's the absolute min. Let's take a look at an example. So find the absolute maximum and minimum values of this function f of xy equals x squared minus 2xy plus 2y on the rectangle D, where x is going from 0 to 3 and y is going from 0 to 2. So we are looking for absolute maxes and mins on this region here. So this is our region D. Now, maxes and mins that we find in this region, they might not be the max and mins for the whole function. But again, we're not looking at the whole function. We're just looking at the portion that lies within this rectangle. Okay, so we're saying within this rectangle, what are the highest and lowest values in here, okay, or along the edge. So to start off, let's find any critical points. So we're going to get, so fx is going to be 2x minus 2y, and fy is going to be negative 2x plus 2. These equations together, the second one, when you set it equal to 0, gives us x equals 1. Plug it into the first one, set it equal to 0, that gives us y equals 1. So our critical point is 1, 1. And for its value, f of 1, 1 is 1. So we're going to hold on to this. Okay, so that's 1, 1. So right in here, we have a critical point with an output of 1. Okay, so we're going to see if that ends up being the largest or smallest of all values. And notice this critical point is within the rectangle. If we got a critical point that was like 5, 7 or something, and it's like way out here, we wouldn't think about it. We would remove it from consideration because it's not in the designated region. Now, this is where we need to kind of step this up a little bit, because now we need to look at the boundary. So as you can see, this rectangle is split up into 4 separate line segments. So I've already labeled them L1, L2, L3, and L4. The reason I've done that is because these are 4 different functions, 4 different curves, so we need to treat them each separately. So we're going to have 4 different curves, okay, 4 different segments that we're going to be looking at. If it was not straight lines, maybe if it was something, you know, like a straight line and like a parabola, or like just like a circle or something, then we wouldn't have to do this 4 times. But in this case, 4 line segments, 4 boundary curves. So we're going to look at the values on the boundary of D, which consists of 4 line segments, L1, L2, L3, and L4. And similarly to the last example, I've already kind of put some of the work in here just so we can get through this a little bit faster. So we're trying to find max and min values. So if we start with L1, on L1, that's the line y equals 0, and x is going from 0 to 3. So if y is 0, then our function becomes f of x comma 0, so just x squared. So the function along this boundary curve is just y equals x squared, basically. So if we're looking for maximum and minimum values, that's going to occur at 0, 0. Okay, that's where this would be the smallest, and the maximum would be 3, 0, because that's where it's the largest. Again, just along L1, just along this line segment. So it's the smallest here, and it's the largest here. Again, this is a parabola, so right, it's going to go up, but again, coming out of the screen at us. So it's going to go up as it moves along from the first to the last point. So those are the max and min for L1. Now, if we go to L2, on L2, x is 3, right? That's the vertical line, x equals 3. So we substitute that in. We get 9 minus 4y, with y going from 0 to 2. So we have on this segment here, we have the function is a linear. It's acting like a line. 9 minus 4y. That is going to be maximized when y is 0, right? Because you're subtracting off a 0 here, so it's 9. That's minimized when y is 2, because then, again, the line is going down as you move along there. So we have our max and min on L2, okay? And we got their outputs along the way as well. For L3, now we're on the horizontal line where y equals 2. So if we go, on L3. L3 is a little bit trickier because we have something that's still quadratic like this. And just looking at this, there's not necessarily like a definitive pattern of, x is going from 0 to 3, but when x is 0, it's 4, but when x is 3, it's 9 minus 12 is negative 3, plus 4 is 1. So it seems like the value might go down, but then other values in between go up, and so it's not as clear-cut as the first one, where it only goes up strictly, or this one, where it only goes down strictly. This one, it has a little bit of up, a little bit of down, right? Some plus, some minus. So the nice thing is we can factor this as x minus 2 squared. So when we're considering the value that would minimize this, the smallest this could be is 0. That would happen when x is 2, right? When x is 2, we get our minimum. And so when would it be the largest? Well, on this interval, it's the furthest value away from 2, which from 0 to 3 would be 0, right? On the number line, 0, 1, 1, 2, 3. So it would be 2 units away instead of just 1 unit away on this side. So our minimum is at x equals 2, so 2, 2, with an output of 0. Our maximum is when x is 0, so we have 0, 2, gives us an output of 4. And lastly, L4, so we're on that vertical line segment, the y-axis. So this one is a lot like the first one. So x is 0, so we get the function is 2y, with y going from 0 to 2. So we end up with the minimum, of course, is at 0, 0, and then the maximum is, of course, at 0, 2. And some of these points repeat, so that's good. So it's kind of, verified in here. So these are all of the max and min values, all of the extreme values along each one of those boundary curves. So on L1, we have an output of 0 and an output of 9. On L2, 1 and 9. On L3, 0 and 4. And on L4, 0 and 4. Now we just need to compare. So compare the outputs from the border and from the critical points. So if I zoom this way out here, we've already found our critical point value, and then we've got our mins and maxes here. We find the largest anywhere, and that's the absolute max. And that's going to be these 9s, and they're the same point. So they share, it's just the same value. The smallest, so no, would be 0, I believe. So that's at 0, 0, and at 2, 2. Okay, and 0, 0 here. Let me do that different color. Okay. Turns out the critical point was not an absolute extrema on this region. There are values larger than it, and there are values smaller than it on this region. So our absolute max is at the point 309. So that's the one that we found on the border there. And the absolute min is shared by 2 points, that is 0, 0, 0, so the origin, and 2, 2, 0. So we have an absolute max and our absolute mins. And just so we can get an idea of kind of what is exactly happening here with all of these calculations, I'm going to pull up the graph. So I'm going to get rid of that one. So this is the function. This is the function that was given in the problem. And you can see the saddle point right there. That was the critical point. We didn't look into whether it was a max or a min or not, but that's the critical point there at 1, 1. So if I swing this around, you can see it's at the point 1, 1 right there. Now, if I go ahead and draw the rectangle, actually, let me, so we can see it a little better. So there's the rectangle right there. That is the region from x going from 0 to 3, y going from 0 to 2. So you can see that right there. So we're only looking at the function within that red rectangle. Now, if I extend this up, you can see it kind of carves out a piece of this graph. So if I set this up and I take away that, this is the piece that it carved out right here. So you can see it lines up vertically. And you can see if I go around it like this, that it stretches all along the curve, but it's still above the region in question. So now let me go ahead and take off the function. Now I think it's a little clearer to see. You can see where the saddle point is, right, at 1, 1. And you can see where these max and min values are. So you can see at 0, 0, we have a min, and at 2, 2, we have a min. And then the maximum, I think, is pretty obvious. It's that really tall one right there. That's at this corner over here on 3, 0. So if I plot those, you can see the points right there. The two absolute mins and the absolute max on this region. So you can see them right there. All right, so this is what we were looking for. So we were taking a piece of the function over a particular region and identifying, using critical points and using the boundary curves, what is the absolute largest and smallest values on the function in this region. And that, after quite a long while, brings us to the end of section 14.7. This is our introduction into finding maximum and minimum values and saddle points. When we come back in the next section, we'll be looking at another method of finding maxes and mins when we have restrictions or constraints that are placed upon us. So I will talk to you all in the next section.